So I'll start covering the chapter of transmission lines in the book of Fawwaz Ulaby. Here is the contents of the chapter. Let's start. The first section is general considerations or things you have to know before starting to learn about this topic. Let's start reading together. In most electrical engineering curricula, the study of electromagnetics is preceded by one or more courses on electrical circuits. In this book, we use this background to build a bridge between circuit theory and electromagnetic theory. So we'll start by comparing electromagnetics with circuits and deal with electromagnetics and use KVL and KCL. By modeling transmission lines in the form of equivalent circuits, we can use Kirchhoff's voltage law and current law to develop wave equations whose solution provide an understanding of wave propagation, standing waves, and power transfer. Familiarity with these concepts facilitates the presentation of material in later chapters. So it's just the basics for something incoming. Although the notion of transmission lines may encompass all structures and media that serves to transfer energy or information between 2 points. So it's a general term that includes nerve fibers in the human body and fluids, and solids that supports the propagation of mechanical pressure waves. This chapter focuses on transmission lines that guide electromagnetic signals. So our concern with this book is electromagnetic waves, so we'll see the transmission lines from the point of view of electromagnetic signals. Such transmission lines include telephone wires, coaxial cables carrying audio and video information to TV sets, or digital data to computer monitors, microstrips printed on microwave circuit boards, and optical fibers carrying light waves for the transmission of data at very high rates. Fundamentally, a transmission line is a two-port network, with each port consisting of 2 terminals, as illustrated in figure 2.1. So as we can see here, it has 2 ports, with each port consisting of 2 terminals. One of the ports, the line's sending end, is connected to a source, also called the generator. So this side is the sending end connected to a generator that generates some voltage in some way. The other port, the line's receiving end, is connected to a load. So here we could consider it's the output of the transmission line, and here we have a load and we have to transmit some kind of power to it. The source connected to the transmission line's sending end may be any circuit generating an output voltage, such as a radar transmitter, an amplifier, or a computer terminal operating in transmission mode. From circuit theory, a DC source can be represented by Thevenin equivalent generator circuit consisting of a generated voltage Vg in series with a generator resistance Rg as shown in figure 2.1. So here if we have DC, we could have a very large circuit that has different things, but we can model it to a Thevenin equivalent in just a source and a resistance. In the case of alternating current, the generator circuit is represented by a voltage phasor and an impedance Zg. So in this figure is the AC version, not the DC one. Here it's represented using a phasor and impedance Zg, not Rg. The load circuit, or simply the load, may be an antenna in the case of radar, a computer terminal operating in the receiving mode, the input terminals of an amplifier, or any output circuit whose input terminals can be represented by an equivalent load impedance ZL. So ZL here is just a representation for any load we can put in here. So when can we use the transmission line model, or why use a transmission line although we have normal circuit model? In low frequency circuits, circuit elements usually are interconnected using simple wires. In the circuit shown in figure 2.2, for example, the generator is connected to a simple RC load via a pair of wires. In view of our definition in the preceding paragraphs of what constitutes a transmission line, we pose the following question. Is the pair of wires between terminals A, A', and terminals B, B' a transmission line? If so, under what set of circumstances should we explicitly treat the pair of wires as a transmission line, as opposed to ignoring their presence altogether and treating the circuit as only an RC load connected to a generator. So what's different in here? Why even we have the concept of transmission lines? The answer to the first question is yes, the pair of wires does constitute a transmission line. So here it constitutes a transmission line. And the answer to the second question is the factors that determine whether or not we should treat the wires as a transmission line are governed by the length of the line and the frequency of the signal provided by the generator. So what decides whether we're going to use the transmission line model or not is the frequency of generator and the length of this line. As we'll see later, the determining factor is the ratio length to the wavelength of the wave propagating on the transmission line between the source and load terminals A and B respectively. So wavelength or lambda is related to the frequency. So what determines whether we use the transmission line model or not is the ratio of the length to the wavelength. If the generated voltage is co-sinusoidal in time, then the voltage across the input terminals is. So if we have a sinusoidal voltage equation, we have the voltage is represented in that way, where omega is 2 pi f is the angular frequency. And if we assume that the current flowing through the wires travel at the speed of light, which is 3 times 10 power 8 meters per second, then the voltage across the output terminals B will have to be delayed in time relative to that across A by time travel delay L over C. So speed is length over time. We have our speed is C, so C equals L over T, and the delay is the time that it takes to travel, so T equals L over C. Thus, assuming no ohmic losses in the transmission line and ignoring other transmission line effects discussed later in this chapter, we could say that the voltage at B is just the voltage at A delayed by the time it takes to travel to reach B. So L over C, okay? And when we plug that into A's equation, we could see that B's equation is V naught cosine omega times the time, which is the main time minus the delay. And we could just say that the delay is phi, which is omega L over C radians. Thus, the time delay associated with the length of the line L manifests itself as a constant phase shift phi node in the argument of the cosine. So this term is constant according to what frequency we use, the length, and C. It doesn't depend on our time. Let us compare VB to VA at time equals 0 for an ultra low frequency electronic circuit operating at frequency 1 kHz for a typical wire length 5 centimeters. We could see that gives us that VA equals V node because cosine 0 is 1 and then VA becomes V node, and VB is V node times cosine the delay is omega L over C, and it gives us this. Plugging it into, you could see that VB is almost equals to V node, which is VA. So here the model of transmission line doesn't really make sense. It's true, but estimation would be also great. So the real numbers are very close to the when we use the transmission line model. So estimation just works. Hence, for all practical purposes, the presence of transmission line may be ignored and terminal A may be treated as identical with terminal B, so far as its voltage is concerned. On the other hand, had the line been 20 kilometers long, so it's way longer than the previous question. So it's now 20 kilometers instead of 5 centimeters, and using the same frequency as the previous, then the same calculation would have led to VB equals 0.9 V node, 0.91 V node. So here there is a difference going from 0.9999 to 0.91, a deviation of 9%. That's significant, and it will result in some changes. The determining factor is the magnitude of phi omega L over C. So here L is very big, so it contributed to having a greater phi. From equation 1.27, the velocity of propagation of traveling wave is related to the oscillation frequency and the wavelength by. So it seems that in the previous chapter they have discussed this equation, and we have to know that the phase velocity is just frequency times the wavelength. Plugging that into our phi, and here our velocity is just the speed of light, we could see that phi could also be represented as 2 pi L over lambda, where L over lambda is very small. Transmission line effects may be ignored, but when L over lambda greater than or equals to 0.01, it may be necessary to account not only for the phase shift due to the time delay, but also for the presence of reflected signals. But what is a reflected signal? We'll see that later in the chapter. a very fast concept here is a wave is propagating that way, and then when it reaches something different, it will start to reflect back. We'll see that more in details later sections. Power loss on the line and dispersive effects may need to be considered as well. A dispersive transmission line is one on which the wave velocity is not constant as a function of the frequency f. So for different frequencies, the velocity is different. So some waves will reach fast and some will reach slow. So the wave at the end will look very different. Also, it depends on how dispersive it is. This means that the shape of a rectangular pulse, which through Fourier analysis can be decomposed into many sinusoidal waves of different frequencies, gets distorted as it travels down the line because its different frequency components do not propagate at the same velocity. Preservation of pulse shape is very important in high-speed data transmission, not only between terminals. Okay, so imagine that you have something and you want to transmit it, and then at the end you see that the pulse reached is very, very different. We have to take that into consideration and see how we could compensate or work with it. Here it's non-dispersive. The initial wave is thus the same as the out, but those two examples, it's dispersive. The final wave is different. So the sentence was, preservation of pulse shape is very important in high-speed data transmission, not only between terminals, but also across transmission line segments fabricated within high-speed integrated circuits. At 10 GHz, for example, the wavelength is 3 centimeters in air, but only on the order of 1 centimeter in a semiconductor material. So we saw earlier that the phase velocity is lambda times f. So if we use the speed of light and frequency 10 gigahertz, this will be 3 centimeters. So the wavelength is very small, and also depends on the material we're working with. So it says that it's in the order of 1 centimeter in semiconductor material. Hence, even lengths between devices on the order of millimeters become significant, and their presence has to be accounted for in the design of the circuit. Propagation modes. A few examples of common types of transmission lines are shown in figure 2.4. So this is the figure we're going to talk about right now. Transmission lines may be classified into two basic types: the transverse electromagnetic transmission lines and high-order ones. Waves propagating along these lines are characterized by electric and magnetic fields that are entirely transverse. So the direction of electric field and magnetic field is perpendicular to the direction of propagation. So electric field is not flowing this way. Instead, it's just perpendicular to the direction of propagation. We'll see an example in just a second. Such an orthogonal configuration is called a TEM mode. A good example is the coaxial line shown in figure 2.5. So this is an example where the electric field is this way, coming from the inner conductor to the outer conductor. It's perpendicular to the direction of propagation, which is out of the page, for example, or into the page, as this is the direction of magnetic field. The electrical field is in the radial direction between the inner and outer conductors, while magnetic field circles the inner conductor, and neither has a component along the line axis, the direction of wave propagation. So here, because neither of them has a component in the direction of propagation, that's why it's in the TEM mode. Other TEM transmission lines include the two-wire line and the parallel plate line, both shown in figure 2.4. So those are other examples. Although the fields present on a microstrip line do not adhere to the same exact definition of a TEM mode, the non-transverse field components are sufficiently small in comparison to the transverse components. So the microstrip line might have components traveling in the direction of propagation, but they're very small, so it's considered TEM. A common feature among TEM lines is that they consist of two parallel conducting surfaces. Higher order transmission lines. Waves propagating along these lines have at least one significant field component in the direction of propagation. Hollow conducting waveguides, dielectric rods, and optical fibers belong to this class of lines. So those are examples, and it says they're discussed more in chapter 8. Only TEM mode transmission lines are treated in this chapter. This is because they are more commonly used in practice, and fortunately, less mathematical rigor is required for treating them than is required for lines that support higher order modes. So we'll start by just seeing the concept itself and then learning about higher order modes later. We start our treatment by representing the transmission lines in terms of a lumped element circuit model, and then we apply Kirchhoff's voltage and current laws to derive a pair of equations governing their behavior known as the telegrapher's equations. By combining these equations, we obtain a wave equation for the voltage and current at any location along the line. So we'll obtain a voltage equation and current equation similar to the wave equation, and we could get the voltage or current in any location on the line. Solution of the wave equations for the sinusoidal steady-state case leads to the set of formulas that can be used for solving a wide range of practical problems. In the latter part of this chapter, we introduced a graphical tool known as Smith's chart, which will make it easier to get different things that we need. We'll see what we need later, which facilitates the solution of transmission line problems without having to perform laborious calculations involving complex numbers. So we'll have a graphical tool and we'll just could get what we need using a ruler, compass, and whatever. We'll see it later. The next section is the lumped element model.